Alright, so what we're going to be looking at is going to be walking through some optimization problems and trying to find the minimum amount of money it costs or the maximum amount of area uh, with a given problem. So we're going to go through, this is the first video of a couple that will go through about 10 different problems that we will be looking at. Okay, so here's the first one. So the first one is a Norman window, has an outline of a semicircle on top of a rectangle. Suppose that you have 8 plus pi feet of wood trim available for all four sides of the rectangle and the semicircle. Find the dimensions of the rectangle, hence the semicircle, to maximize the area of the window. So the reason you'd want to probably maximize the area of the window is so that you can get the most light in, which is the main reason what a window is for. So a normal window looks something like this. Alright. And its dimensions that we're going to label, we're going to say that the height is y, and we're going to say that the length is 2x. Now the reason it's 2x is because the diameter of the top circle, of that semicircle, we're going to say is x. And so the radius is x, so the diameter has to be 2x. Now, the information it gives us is it talks about the perimeter. Well, the perimeter of this would be the perimeter of the rectangle, which would be 2y plus 4x. Right. And we're going to add that to the perimeter of the top. So we're going to go half the circumference. So it'd be, what is it, 2, circumference is 2 pi r, and we're going to divide that in half, so it would be pi x, okay, because the radius is x. And that equals 8 plus pi feet. Okay. And now it wants us to maximize the area. So the area of this would be 2xy, area of the rectangle, plus the area of the semicircle, which would be pi r squared all over 2. Okay? Or pi x squared, because the radius is x. And so now what we're going to do is that we're going to solve for one of the variables here and plug it into that area formula. And then we're going to optimize it. And so the easier one to solve here would be the y. Okay, so we're going to solve for y. Move these to the other side, divide by 2, getting us y is equal to approximately 8 plus pi minus parenthesis 4x, no, not 4x, 4 plus pi parenthesis x all over 2. Okay. Now we're going to take this and plug it into that area formula and for the y values. So that means our area will be equal to x times 8 plus y minus 4 plus pi x plus pi x squared all over 2. Okay. And now what we're going to do is that we're going to take the derivative of this after we simplify it and everything. So what we have is, once we multiply everything in, we'd have a is equal to 8x plus pi x minus 4 plus pi x squared plus pi over 2 x squared. Take the derivative, so a prime, which would be 8 plus pi minus 2 4 plus pi x plus pi x. Now what we'd want to do is get x by itself. Okay. And so when we get x by itself, or let's simplify this. Let's see if we can get it even smaller. So we'd have 8 plus pi minus 8 minus 2 pi, and both these have x's attached to them, plus pi x. Okay. Let's see here. We are going to combine these two right here, which will get us a negative pi x. And we have 8x minus pi plus 8 equals a prime. Okay. So now I'm going to move this to the other side, and I'm going to factor out an x here and then divide it over. And what we end up getting is negative 8 pi, negative 8 minus pi all over negative 8 minus pi. is equal to x, which means x has to equal 1. So the bottom part, or the radius of this, would be 1. And then after that we plug this one into our formula down here to find what y would be. And we end up finding out that y would end up being 8 plus pi minus 4 minus pi all over 2, which would be y is equal to 2. So y would be 2 feet, x would be 1 foot, but it wants the dimensions of the rectangle, okay, dimensions of the rectangle. So our answer would be 2 by 2, or in other words, it is a square. So it's 2 feet by 2 feet square for this Norman window. So again, whenever you want to optimize, what you're trying to do is you're trying to you get the formulas and then you zero out the derivative and then find where you're going to maximize or minimize whatever it is you want to find. So now this next one, what we have is that we're going to be making a cylinder barrel for Dr. Brent, who wants to float over Niagara Falls for some reason, which we don't know why. Maybe we don't like Mr. Brent, so we're going to do it to him. But anyway, what we have is that we know that he can fit into a 1 cubic meter barrel. And so we're going to try to make a barrel that is 1 cubic meter in size, and we want to minimize the cost of it because the lateral area, or the lateral surface area, costs about 18 feet per square meter, and the circular tops are 9 square feet, or square meters. 9 feet, $9 per square meter. And so we have our cylinder, okay, giving our little dimensions, h by r. Okay. And so we know that the volume is going to equal 1, and the volume of a cylinder is pi r squared h. Okay. And now the area of the circles, or the area of the top part, would be pi r squared. The lateral area will be 2 pi r h. Okay, so the circumference of the circle multiplied by the height. And the cost of making this, which is what we're trying to minimize, will be $18 times the lateral area, 2 pi rh, plus $9 times, there's 2 of them. Right. So there's 2 circles. So 2 pi r squared. Okay, and so we're going to try to minimize this. Now, what we're going to want to do is that we got to replace either the r or the h. And so the easier one to do will be to replace the h, because then we don't have to deal with a square root. So we know that h will equal 1 over pi r squared, and that's just solving for h there. Now that h gets plugged in, or this gets plugged in for the h here, and then we simplify. Well, this becomes 36 pi rh plus 18 pi r squared, just so we can keep the numbers together. And so what we have is that our cost will equal 36 pi r all over pi r squared plus 18 pi r squared. And so when we reduce, the pi's cancel, this r is gone and one of those r's are gone. So our new cost will be 36 all over r plus 18 pi r squared. And now we're going to take the derivative of it. Okay, so we're going to go c prime would be negative 36 all over r squared, which is the derivative of the first half, plus 36 pi r, which is the derivative of the second half. We zero this out, so 0 equals a negative 36 all over r squared plus 36 pi r. which gets us a 36 over r squared is equal to 36 pi r. Solving for r, so we've got to move this r to the other side. So when we move this r to the other side, we end up getting a 36 is equal to 36 pi r cubed. Solving for it, we end up getting our r is equal to 1 over the cube root of pi. Okay. So that's what our r is. And now, that's one of our answers. So the r. That's our exact radius. And now it wants the exact height. So we're going to take this r and plug it into there. Okay. Now this is where you're going to have to do some algebra manipulation to try to get a nice round number. And so our h is equal to 1 over pi 1 over the cube root of pi squared. Since we are dividing by a fraction, we flip and multiply. H is equal to 1 over pi times pi to the 2/3 over 1. Okay. So we end up having h is equal to pi 2/3 all over pi to the first. Reduce this, and we get our answer of y, or h is equal to 1 over the cube root of pi. Or when we reduce this, we had 1 over x to the 1/3, which is the cube root. And these are both in meters. So that means that our barrel, to minimize our cost, okay, would be 1 in a cube, 1 over pi over 3 in the radius, and 1 over the cube root of pi for its height. Okay, and so that would be our answer for those. So now the next one. So we've got a rectangular sheet of paper who has a perimeter of 36 is rolled into a cylinder. What's the dimensions of the sheet that gives the largest volume? So the volume of a cylinder is pi r squared h. The perimeter of the paper is 36, and to find the perimeter, it would be 2x plus 2y. Okay, we're saying that our dimensions are 2x, 2y. Let's reverse this. Let's say this is, or we'll say this is x and this is y. And so we know that we are going to be constricted by saying x plus y must be 18. Okay, so x plus y has to be 18. And so what we have here is that for us to find what the radius is, x is the perimeter of a circle. The perimeter of a circle is 2 pi r, so that equals x. Okay. Volume deals with h, or r squared h. Well, h is y in this case. That's our height. And so now to find what r is, we solve this, which gets us r is equal to x over 2 pi r, or 2 pi, x over 2 pi. So now we have our answer as, if we take this r and plug it in here with the y, we end up having our volume is equal to pi times y times x all over, or x squared, because we've got to square it, all over 4 pi squared, which reduces down to y x squared all over 4 pi. So that is our volume. Okay. Now what we have to do is that we have to substitute our constraint in. So we're going to say x is equal to 18, or no, we're going to say y is equal to 18 minus x. Plug that in for the y, which gets us 18 minus x, x squared, all over 4 pi. Reducing that gets us an 18x squared minus x cubed all over 4 pi. Now we want to try to maximize it. So what we're going to do is that we're going to take the derivative of it. So v prime is equal to 36x minus 3x squared all over 4 pi. Set that equal to 0. Okay. All we have to worry about is the top part. So our answers, so one answer is going to be x equals 0 for sure, because if we plug in a 0 for the top, for either of those it gets it. And our other one would be 36 minus 3x equals 0, which would be 3x is equal to 36, which means x is equal to 12. Okay. So x is equal to 12. So if x is equal to 12, that means that the y must be 6, okay, because of that. So now that would be the dimensions of the sheet. That will maximize our volume. Okay, pretty easy, pretty straightforward. The hardest thing here is just remember setting up your problems and getting everything set.